So we offer free design advice and analysis advice, mainly to UNSW researchers and HDR students. We also offer statistical review of grant and ethics proposals. Finally, we have short courses as well as monthly seminars, which you can find on our website. And of course, if you're here, then this is our monthly seminar, and it's monthly. So finally, we also have partnerships and contracts if you have some bigger jobs that you want to hire us for. So today, for our monthly seminar, we have our very own Ben Maslin. He'll be talking to us a bit about generalized additive models. So take it away, Ben.
He's good. Does he know he's
Ben, I think you're...
Okay. Can you hear me?
Yep.
Yes.
Okay, great. Okay, well, welcome everyone. Yeah, as Nixon said, I'm going to be talking to you guys about splines and generalized additive models, basically what to do when your data isn't linear and playing nicely. Okay, so we'll start off talking about linear regression, then we'll go into polynomial terms that you can put into a linear model, spline smoothers and generalized additive models and some extensions to these. So talking about cyclic variables or cyclic smoothers, interactions of smoothers, you can do random effects, you can have different responses, and then we'll go through a real data example with some CO2 data, and then some resources at the end. If you have any questions at all, just send them into the chat or ask at any point. Just unmute yourself and talk. If you're in person, I don't know if it'll necessarily come through for me online, but you can just put your hand up and Nixon can get the question asked, so I can hear as well. And there'll be time for questions at the end as well. Okay, so let's get into it. So as I'm going through this lecture or the seminar, I'm going to be giving some examples of some code in R. R isn't the only software that you can fit these kinds of models in. You can do it in Stata, SAS, Python, and MATLAB. As far as I'm aware, though, you can't do it in SPSS, so keep that in mind. There's also great software for fitting these kinds of models in R. There's a MGCV package that's got a lot of flexibility. You can do quite a lot with it. And it's also my software of choice as well. Okay, so let's start off here with the basics of a linear model. Okay, so we have this relationship that we're assuming to be linear, and we're trying to estimate this linear trend. Okay, the assumption is in this equation here, equation of a straight line with some error terms. So we have yi is equal to beta naught plus beta 1 xi plus this error term, residuals. Okay, beta 1 here represents the slope or the gradient of the line, and we interpret it as a 1 unit change in our predictor x is how much y changes. That's what we interpret beta 1 as, and beta naught here is the intercept, which we're generally not that interested in. And then here we have some our residuals, okay, the error term here. Now, because data is always noisy, it's not going to just be a perfect linear relationship here. So this sort of captures that noise, and we assume that noise to be Gaussian or normally distributed with mean 0 and constant variance. So we're assuming it's evenly spread above and below this line, okay? And the residuals you can see in this plot is basically the distance from these points to the fitted line. And we've also got a band here. This is like our confidence interval around our mean slope value. Okay, so whenever we're doing inference, we're assuming we're trying to estimate a linear relationship here. There's a bunch of assumptions that we need to make for this model, okay? Firstly, that our observed y values are independent after accounting for our predictor x, that the residuals that we talked about before are normally distributed with mean, zero, and constant variance, so that variance doesn't change across our y values or our fitted values. And lastly, there's a straight line relationship between the mean of y and each x variable. Okay. Now, whenever we do some, more complicated stats that isn't a linear model, it's generally because one of these assumptions has failed, or we can't satisfy it, and we need to relax that assumption by fitting this new method in order for the assumptions then to be satisfied. And that's where we come in for this lecture. For this assumption here isn't always satisfied. You don't always get this nice linear relationship. So in that case, what do we do? Well, first we should check this assumption. How do we check it? So we can check this last assumption by plotting our model residuals against our fitted values. And if there is a straight line relationship, there should be no obvious pattern in this plot. So we've got our residuals on our y-axis, our fitted values, which is the estimated line that we fit on the x-axis here, okay? And we're looking for any like U-bend or patterning here that seems to suggest that we haven't actually captured the general trend, okay? So let's look at an example where the data isn't playing so nicely, okay? So in this instance here, we're trying to fit a straight line, and it doesn't really look like the data is that linear. It may be looking a bit more quadratic, and you can see that here with all these points sort of being above the line here and on the ends. And you can see this more clearly when we plot the model residuals against the fitted values, and you get this clear U-bend here in our residual versus fits plot. Okay, so based on that, I would say that our assumption of linearity isn't satisfied here, okay? So that violates one of our model assumptions. So any resulting inference is no longer going to be valid. We're not really capturing what the data is actually showing, okay? So instead of assuming it's a linear model, we could try and assume it's a quadratic model by having a quadratic term in our model, okay? So we're just going to add a beta 2 xi squared here in our model. And this is pretty simple to do in R. You can use the poly function here and just put a 2 as the degree of our polynomial to fit a quadratic. And we can see what we end up with looks much more accurate. We're now, following the trend of the data a lot more nicely, okay? So that looks good. And we can have a look at a residual versus fits plot as well. And this looks really good as well, okay? Although we've got more points on the left-hand side and the right, that doesn't really matter. That's not what that doesn't violate an assumption. That's just where the data is sitting, okay? But what we're interested in is now this U-bend is no longer there in our residual versus fits plot. So this is looking like we're capturing the trend of the data a lot better. You don't have to stop at quadratic terms. You can also fit higher order polynomials. You can just, again, use the poly argument, change the degree. So for instance, we could fit a cubic polynomial as such, okay? What if our data looks like this? If it's quite wiggly and we want to estimate this wiggly relationship, it starts to get a bit cumbersome trying to work out, the degree of a polynomial you need and how you interpret that and get predictions. It's not a fix-all, okay? So what if our data looks like this? Well, this is where spline smoothers and generalized additive models come in, okay? So a spline smoother estimates wiggly relationships by fitting a smooth function to your predictor variable. So it changes from our linear model, where we're assuming we have a yi equals beta naught plus beta 1 xi relationship. We now replace this beta 1 xi with a function. So instead of assuming a straight line relationship, we're going to assume that there's some function of our predictor variable x, okay? And we're going to estimate this function. And Yeah, and so the term spline actually comes from woodworking, especially shipbuilding, and the problem of bending straight sections of wood to form curves. And it's because traditional splines would break your explanatory variable into sections at knots and fit multiple regression against all of these sections. This is done by fixing at control points or knots. It's commonly done now, and there's lots of different ways to do splines, so this isn't necessarily what everyone does, but this is the default in MGCV, and a lot of different splines are doing something somewhat similar to this, is using basis functions. Okay, it's so this is doing this is what the default in MGCV is doing, thin plate regression splines, and using basis functions to estimate our smooth spline. So we have a bunch of functions, Zj, okay, and we're going to get a weighted sum, or like a weighted average, if you want to call it, of all of these, well, it's weighted sum of all of these basis functions, and that's what's going to estimate our spline, okay? And we can fit this thin plate regression spline in R using the MGCV package. And all we have to do is, instead of having LM here as our linear model in R, we're going to use the GAM function from the MGCV package, and we're just going to put an S around our X variable, okay? And that's just going to tell the function to fit a spline or estimate a spline smoother for that predictor variable. You'll also notice that I've put in here method equals REML. That stands for restricted maximum likelihood, and it's generally a good idea to use this when you're using GAMs to get more accurate estimates of the model parameters. But keep in mind that this isn't a good idea if you're doing likelihood ratio tests or using information criteria for model selection like AIC or BIC, because restricted maximum likelihoods are not directly comparable between models with different fixed effects. Okay, so we're going to fit this spline smoother to our data using that code, and it looks pretty good. Okay, we're fitting the trend of the data quite nicely. We've got this nice wiggly relationship. Okay, and it's looking pretty good. Okay, and we can look at what's going on under the hood here by plotting the basis functions. So it looks quite odd, but this is how our black curve is actually estimated. It's using all these other functions here and does like a weighted sum of all those functions, and that's how we get this this black line here, which is interesting. Okay, and an important thing to consider is this k argument. Okay, so we can control the number of basis functions used to estimate our splines using the argument k. Okay, so changing k alters the complexity or the wiggliness of our estimated function. So for instance, if we were to use k equals 3, we'd get a much less wiggly curve. Okay, it's trying to fit to the data, but it's struggling. Okay, it doesn't have enough terms or enough basis functions to accurately capture this wiggly relationship. Okay, and you can see what it's struggling. It's only got these two basis functions here, and this is the best that it can come up with. Okay, so it's always 1 minus k number of basis functions. K minus 1, I should say. Now, most spline smoothers also include a penalty for wiggliness. So this means that they will prefer a smooth fit unless the additional wiggliness provides enough of an improvement in fit that it overcomes this penalty. So k is really an upper limit of how wiggly the curve can be. So it's not necessarily going to get more and more and more wiggly all the time as you increase k. So for example, this is k equals 10 versus k equals 50. Doesn't change. It's a little bit more wiggly, but not too much. And the choice of k can be thought of as a model selection problem. It's the default k, and my software isn't always appropriate. Sometimes you're not able to, k isn't large enough and you're not able to capture the general trend. And other times k is too large and you're overfitting your data. So you could use things like information criteria or checking residual versus fits plots and so on to try and help choose the most appropriate K for your data. As with any inference, it's always good to check your model assumptions. Okay, there's a gam.check function in the MGCV package, and that's quite useful to get out all your model assumption plots. So we've got our QQ plot here. I mean, the most important two are just these two here, really, is your QQ plot. Check that your residuals are falling along the diagonal line to ensure that you've got that the Gaussian assumption is appropriate. And we have our residuals versus our fitted values here as well, which also looks good. Okay. We can also have a look at our model estimates using the summary function in R. So we do summary of our fitted GAM. We get this output here. Okay, and we get a whole bunch of things, but basically it generally groups the fitted parameters into the parametric coefficients and the smooth terms, the splines. Okay, so in a GAM you can put in, linear relationships like as you would in a normal in a linear model, as well as wiggly terms, factor variables. It's very flexible. You can put a lot of things into it, and this is where it'll come out. So we've got our our estimate for the intercept term, which isn't really of interest to us, and we have our smooth term, a p-value for whether there's evidence to suggest that there is some sort of wiggly relationship in our data, and F statistic for that test. You see, we have this EDF thing here. This is the estimated degrees of freedom. So this is a good indicator of how wiggly your relationship is. It can also be a good check if the EDF is 1, you're just fitting a linear line, even though you with all these basis functions and things, so you're better off just doing a linear model anyway. Yeah. Okay. So now we're going to be talking about some extensions to GAMs. Okay, so sometimes you're wanting to fit relationships on a predictor variable that doesn't have a clear start and an end. Okay, so like radians on a circle or days of years, you're going across lots of years. Okay, and you want basically in a plot the ends of the line to basically join up, and you can do this in MGCV using a cyclic cubic regression spline. And you just need to put in the BS equals CC argument inside our spline function call here. And then we're going to fit a cyclic spline. And it looks very similar to what was plotted before. But the difference here is now this end, the left and the right ends basically join up together. Okay. Yeah. So you can also fit interactions. So spline smoothers are sometimes called additive models or generalized additive models, but they don't need to be additive. You can also include interactions as well, and interactions with both categorical variables as well as continuous variables. So you can have different smooths for each level of a categorical variable. Say by having a smooth of x1 by x2, where x2 is a categorical variable with a bunch of different levels, and two-dimensional smooths for two continuous variables. Okay, and you can do that just using our S call if they're on the same scale, or you can do a tensor smoother if they're on different scales. Okay, so let's have a look at what this is doing in practice. So we can do interaction with a categorical variable. So we're going to fit a bunch of different wiggly relationships, okay, by this group variable, okay, and we get all these different wiggly curves depending on what group you're in. This is the different relationships that you have. So you could do something like this for, longitudinal or other relationships where you're looking at trends over time, for example, across different groups, and you expect those different groups to have different non-linear relationships. You can also, as I said before, you could fit a continuous interaction between an interaction between two continuous variables. We're going to use a tensor smoother here, and we can have a look at what this looks like. It's fitting a surface, basically. So our fitted values depend on this surface, basically, and the values of x1 and x2 along this fitted surface. So generalized additive models, the generalized component, we can fit non-normal outcomes. So we don't have to assume we have a Gaussian response in a GAM either. You can have, a response of counts or binary outcomes, bunch of different things. And you can do this in R with MGCV using the family argument, even ordinal responses. It's very, very flexible. There's a lot of people who, think GAM, everything's a GAM. You can do everything with a GAM is in the camp of a lot of people. May not, Anyway, so you can also have random effects in there as well. So you can also have a factor variable with random intercepts just by using the BS equals RE term in your S call. And if you're looking at more complex random effect structures, there's the GAMM4 package or the GAM LSS packages in R, which can use most of MGCV's smoothing terms and use some syntax random effects that you might be familiar with if you've used the LME4 package or GLMM TMB package. You can also fit spatial point process models using a GAM. So if you're interested in modeling spatial point data, so for example, it's common in ecology when researchers go out and they, count a bunch of animals and, the spatial location of those animals. And you want to try and you have a bunch of environmental predictors, and you're trying to predict where, the distribution for where these animals generally live. Okay. And a log Gaussian Cox process is a good way to do it. And it's usually quite hard and difficult, and the software is confusing to fit these models. And Elliot, one of our statisticians at SAS Central, found out you can just do this using a GAM. And that's pretty awesome. And you can find out more details by reading his paper, or you could talk to him or have a meeting with him and learn more about it. All right. So we've talked a lot about GAMs and what GAMs can do. So let's try and use a GAM for a real life data example and see how we go at capturing a real life trend. Okay. So there is a observatory, Mauna Lau Observatory. I don't know if I'm pronouncing that correctly. In Hawaii, I'm pretty sure. And they measure atmospheric concentrations of CO2 in parts per million monthly from 1959 to 1997. Okay, so we have this data set with CO2 concentration values, the year, the month, and then just an indicator of the time. So a monthly indicator that increases across all the years and months. Okay, and we want to try and fit a model that captures a trend of CO2 over time. So this is just plotting the raw data. I could have plotted it as points, but I'm just going to join all the points together because it looks quite messy otherwise. But this is the raw data. This is what the raw data looks like, okay, of CO2 concentration over time. And you can see we have this overall trend where CO2 concentration levels are increasing over time because we're burning fossil fuels. And you also see this trend within a year as well. And correct me if I'm wrong, but I'm pretty sure this is from deciduous trees losing their leaves in autumn and winter and not being able to take CO2 out of the atmosphere. And that's why you see that dip and then that rise again. Yeah. So we want to try and use time to capture this trend. Okay. So we could do something silly. It's clearly not a linear relationship because of that, within a year trend or that monthly trend within a year. It's very wiggly, but we're going to try and fit a linear model to it anyway and see at least whether that captures the general trend. Okay, is the general trend at least linear? Let's have a look at that. So we're going to fit a linear model in R with time and CO2. Okay, so CO2 is our response and time is our predictor. And okay, obviously it looks pretty bad here because we're not capturing that wiggly trend. But what maybe isn't so clear is we're not capturing the overall trend either. The overall trend is also like not linear at all. You can see that we've got this really clear U bend in the data. So the overall trend is also not linear. So let's fit a GAM. Let's have a go with a GAM. So we're going to fit a GAM. Okay. So we're just going to put an S around our time instead of just fitting a straight line relationship to time and see if we can do that. And okay, yeah, we're capturing the general trend. It's going through the middle of all of these wiggly curves across the months, but we're not capturing what's happening within a year very well at all. Okay, so it's not wiggly enough for me at the moment. I want it to be more wigglier. So maybe we should increase K. We're going to set K to 100. And unfortunately, this also doesn't help us. We're still not able to capture this trend, okay? So what else can we do? So let's go back and look at the data. Before we were just modeling time, but we've got year and month, okay? We want to capture what's going on within a year. So let's use that month information and see if we can capture this trend better. So what we're going to do is we are going to have a cyclic term in here for month, okay, so that we start, December and January are very close together. We don't want to end up at two completely different points. We're going to get a cyclic cubic regression spline here for month, and we're going to get an overall trend for year, or I could have put in an overall trend for time as well, okay? And what we end up here, red is the raw data, and you can barely see it because our fitted GAM, our fitted spline smoothers here have very accurately, well, they've done a pretty good job at capturing what this trend is saying. Just using year and month, we're able to capture what's going on with CO2, which is pretty cool. So this is pretty good. Okay, and we can check our assumptions. So the QQ plot looks pretty good here. Our residuals are going along the diagonal line in the first plot. On the plot in the top right-hand corner is our residuals versus fits plot. That also looks pretty good. There's no clear U bend. There's no fan shape. I'm pretty happy with this at the moment. And we can have a look at the model output. And you can see now we have a year and a month term in our smooth part here in our summary output. Okay. And yeah, there's evidence to suggest there is a year effect, and there's evidence to suggest that there is a month effect. So, final tips. There's a tweet by Gavin Simpson who said that GAMs just simplified everything. That if you want maybe some takeaways, GAMs are just GLMs, generalized linear models. GAMs fit wiggly terms. Use plus SX in your not X in your syntax. Use method equals REML, and always look at gam.check. Some resources. There's a good introduction to GAMs on the environmental computing website, which is run by UNSW, and this section was written by Mitch Lyons, who's a researcher here at UNSW as well. There's some code there if you want to plot your basis functions, your GAM in R. That's where I got my code from. Simon Wood, who helped create the MGCV package, has a website which a bunch of helpful resources. And he's also written a book called Generalized Additive Models, An Introduction with R, second edition. Okay. Does anyone have any questions?
Yeah, thanks, man. Thanks for the great talk. If anyone in the room has any questions, you can let me know and I'll try to translate it to Ben as well. Yes?
How do you extract the estimate of the spline term, but instead of the general?
Okay, so the question is, how can you extract the estimate of the spline terms and the standard errors of the spline terms from the output?
How can you extract the estimates of the spline terms? So you can get out the fitted values of everything, of what your fitted model is. You can also use the predict function is a useful thing to see how your estimate changes depending on a range of different values of your term. Yeah, that's how I do it. You can, yeah, there's calls in the summary output and the model output to get out the standard errors and things like that as well.
That means you have to include exposure term, the main study interest in the model, in addition to the spline term.
So the question is, does that mean you have to include your main study effect of interest in addition to other spline terms inside the model?
Yes, yeah. If what you need, like if you have a question of interest, that's your main question of interest, and you're just trying to control for some covariate that has some wiggly relationship, then yes, I would have both your question, your predictor that you're most interested in your model, as well as the things that you're trying to control for that might have a wiggly relationship. And then you're conditionally testing for whether there's an effect on your predictor of interest after controlling for your wiggly covariates. Does that answer the question?
Yes, thank you, Ben.
Yeah, great. We have a question from Elliot, who I name dropped in the lecture series.
Yeah, thanks for that, Ben. Appreciate that. But I was just going to jump on the back of the getting pragmatically getting out your wiggly terms with the predict function there that Ben mentioned. There's an argument in there, type. You can say type equals terms, and that will produce a prediction of each individual term, so you can actually inspect your individual sort of smooths and other terms. And yeah, if you double that up with SE equals true, it'll give you kind of a measure of uncertainty on those. But how accurate those measures of uncertainty are probably a topic for another talk.
Yeah. Thanks, Elliot. We've also got another question in the chat. I wonder if the interaction between intervention and a continuous variable could be used in a game as well. Yes, yep, you can have, if intervention is a fixed effect, you can definitely have an interaction between intervention and a continuous variable as a game. Dr. Harris has a question as well.
Yeah, hi, sorry, I'm just going to ask this question, not sure how relevant it is, but I just put some information in the chat. My question is that when you're looking like a longitudinal observation of the variable or trend, is it possible for that trend to have both linear and quadratic trend at the same time, which might be significant for both? Is this possible? Because I got it in my data. If you look into the chat information that I put,
it's not loading, or not loading for me. I can see that you sent an image, but basically, yes, in my example, one of the for relationships in my by variable was a linear relationship. It will fit it. So I can share screen.
Yep.
So for example, okay, here.
Yep.
This
I can
last
see.
relationship here is on the bottom right-hand corner is a linear relationship. So it's fit a linear line here for that one where it thinks it's a linear relationship. What's hard, I don't know whether you can pre-specify what's linear and what's not, or and also the model output's different because it's still fitting a function. So you're not getting like as interpretable or easy to work with output that you would from a linear model or a linear mixed model, I guess. Yeah.
So if you would like to report on it, like one of the variables of mine has got the significance linear trend of 0.015 and quadratic of 0.017. So if you would like to put it in the words or report it, how would you report? Do you present both, or you just go with the most significant, like quadratic trend? What would be the best approach?
If there's multiple, I wouldn't put in both. Like if you're
Yep.
choosing between two things, I mean, you could put in both if you wanted to do like a sensitivity analysis at the end of a paper or something, just as a as an aside thing to see how sensitive your choice was choosing between doing a linear or a quadratic thing. But in your main table, I would just pick the whatever one is more appropriate. And to look at that, you'd look at your residual versus fits plot, your prior understanding for the dynamics of the system, whether it makes sense for it to be linear to begin with, as well as what the data is trying to tell you. And it can also be a difficult thing because it's not a good idea to do model selection prior to hypothesis testing. And Peter gave a talk. You can see that in one of our monthly seminars on our YouTube. And so sometimes trying to decide between all these different things and then doing a hypothesis test can seem like you're getting into that trap as well. But I think if it's just small decisions it's not good to do something that isn't appropriate for your data, basically. Yeah. So it's if the data isn't linear and it's more appropriate to fit a quadratic thing, then I would do a quadratic relationship and put that in your main table. And if you're unsure about it, you could do a sensitivity analysis and do both and talk about the difference in the results in your sensitivity analysis.
Thanks so much, Ben. That was very helpful. Thank you.
Any other questions? Oh, yes. Can we access your slides? Yes, the slides will be put up online. There's some, our website is a little bit in limbo at the moment. It's going through a new system, but so if it's not up there straight away, it will be up there eventually, but it will be up on our YouTube at least. And it will be on our website eventually. Okay, does anyone else have any questions? Oh, and Anne said that we'll send out the slides and the recordings as well.
No more questions in the room.
Great. Okay. Well, thank you, everyone.
Thanks, Ben.
Thanks, Ben. Thank you so much. Is that central?
Yeah, thanks, guys. Have a good one.
Bye. Thank you. Bye.
You guys are coming? Yeah, I think we're not going to. Okay. This is the line intentional. Maybe our. Now with all the partners here. Just some slides.
Oh, not. That's right. And another thing is, I'll say, maybe I, but. Yeah, that this one. Done by status. Oh, yeah. There's not the list was for all of us. And my email is not correct. My name is not correct. And my email is not correct. So that might be great. I'll go twice again. Show down. That's it. Go all the way down. I know you. No? Because I have.
Oh, wait, this is the minutes, so maybe.
That's right. Well, that one.
Yeah.
So my name is Ron.